Thanks, Luca. Good morning, everyone, and welcome to the talk. So in this talk, I'm going to talk about materials property predictions using machine learning, and this is very broad topic. So more specifically, after a brief overview of the field, I plan to cover two specific examples where we'll see where we use machine learning to predict material properties which are computationally expensive and difficult to compute otherwise. And machine learning based surrogate models allow us to efficiently predict these properties, and therefore we can explore much larger part of chemical space. And so that's where the power of machine learning really comes in. So let's get started. So to this audience, I don't need to convince that we are really living in the age of big data, where machine learning models trained on this data are changing our everyday life experiences. And in transportation, self-driving cars are already a reality. Then we have several other examples like recommender systems on these websites seem to know much more about their consumers than the consumers themselves seem to know. And facial recognition, board games, so artificial intelligence trained programs have actually outperformed many of the best players on the planet in some of these games like chess and AlphaGo. Medical applications, here a specific example is neuron activity mapping, but if you are a physician looking for an assistant, then IBM Watson is already an option these days. And there are many other examples. So this situation is very recent, but if we look in the past, we can find numerous examples where creative use of data has enabled many science and engineering fields. So some examples are again highlighted here. So steel production in India and Sri Lanka actually benefited from this data-enabled learning and of processing parameters. And there is a very beautiful book about this. It's called The Rustless Wonder by T. Anantharaman, if you are interested in this. Then Kepler's law of planetary motion was definitely benefited from lots of astronomical data that was available at that point of time. One of my favorite example is data-enabled nursing by Florence Nightingale. She was very creative in visualizing data, and she actually came up with these plots, these slight modification of pie charts, and then she used these plots to visualize mortality rates due to different causes of deaths. And one of them was infectious diseases, of course, and she showed that once sanitary measures were taken, deaths due to infectious diseases actually came down, and because of her work, she was able to save many lives because of this. Another example is periodic table. At the time of Mendeleev, there were 56 or so elements were known, and there were white spots in the periodic table. So though the elemental species were not known, the presence was very much clear, and in some cases it was also very clear that what kind of chemical properties this particular elemental species will have, and that actually expedite the discovery. And there are many other examples. If you are a material scientist or metallurgical scientist, you are very familiar with these Hume-Rothery rules of solubility, metal solubility, and Hall-Petch relationship connecting strength in polycrystalline materials with average grain size. Toward the end of late 20th century, we have seen developments in both cheminformatics and bioinformatics, and little bit of polymer informatics as well. And now we are seeing something, this data-enabled revolution in material science. And in fact, this has actually been referred to as fourth paradigm shift. The other three being the experimental, theoretical, and computational paradigms. And we are again seeing a paradigm shift where fundamental ways in which material science is progressing is changing right now. And this paradigm shift is mainly brought about by several factors. Some factors are outlined here. So mainly sustained growth in computational power over 50 years or so. Also, algorithmic and method developments, high throughput experiments are also catching up very quickly now. And initiatives like Materials Genome have certainly helped the community getting excited about this. So as a result of all this, how material scientists use, process, generate, and share data is fundamentally changing in a gradual way. And we see indeed there are lots of materials databases that are available online today for everyone to explore. Some of them were actually there before the Materials Genome Initiative, but most of them are very new. And of course, I should add that Nomad is much more than a database, of course. And by this time, you have already realized that. There are also scientific journals where you can publish your carefully generated and well-documented data sets, like scientific data. So we have lots of materials data. And the bigger challenge now is how do we extract knowledge from this data? How do we identify design rules or hidden patterns that will eventually help us discovering better materials? And that's where the machine learning comes in the picture. So very simply, of course, there are lots of details here, but in a very simple manner, machine learning enables us to find an alternative mapping going from materials to the property via this fingerprint. And this is usually oftentimes much more efficient than the conventional routes, either by experiments or first principle computations. And if this is done right, if we use best practices of data science and statistical learning, then we can actually form many cases it's possible to form an alternative mapping which is very predictive. And in addition to allowing us to explore the chemical space in much more efficient manner, it also enables us to answer the inverse design route. So how do we go from property to materials? And that's the inverse design, and via either efficient enumeration or optimization or adaptive design. So my recent work at LANL, as well as in collaboration with Dr. Rampi Ramprasad's group at UConn, have focused on applying this technique to materials problem, and we have many applications ranging from designing polymer dielectrics to understanding factors that control radiation resistance in complex oxides. Also coming up with surrogate models for band gap predictions and dielectric breakdown strength predictions using machine learning models trained on first principles data. So I'll not have time to go into each one of these, but in this talk I'm going to mainly focus on these two particular examples. And I have chosen these two specific examples because these are kind of philosophically very different. So in the first example, we use machine learning, but the emphasis is on getting insights. So it's very physically motivated. We want to understand the mechanism, and we want to choose features in such a manner that we can make predictions which we can understand on the mechanistic understanding. And we are not really looking for very accurate predictions or fitting the curve without really understanding what's going on there. In the second case, we are the goal is to predict the band gaps, and here the goal is really to come up with the best possible fits. So we really want to minimize the RMS error, and we want to predict the band gaps as accurate as possible. Also, in the first case, we use linear machine learning models, but all the non-linearity will be in the feature space. So we really expand our primary features by using non-linear functions. In the second case, we use very simple primary features, and all the non-linearity is going to be in the machine learning model itself. So just wanted to mention this. So let's get started with the first example. And this is the prediction of intrinsic breakdown field strength from using machine learning. So let me take a step back and explain what do I mean by intrinsic breakdown field strength. So what do I mean by breakdown? So let's say we have an insulator and we put it in between two metal plates and we apply an electric field. And then we start cranking up the electric field. at some point insulator is going to break down. That means it will start behaving like a metal. And this critical field is known as the critical breakdown field strength, or the dielectric breakdown field strength. Now, this is a very complex property. It depends both on intrinsic and extrinsic factors. During this talk, I'm going to focus only on the intrinsic factors, which is the breakdown field strength, purely determined by chemistry, and which in itself is a very computationally expensive property. It's very complex to compute, but the mathematical framework that one needs is already available, and it goes back to Froelich and von Hippel's work in 1940s. It's so computationally expensive because one needs to compute the electron-phonon coupling matrix, because breakdown is actually given by balance between electron energy gain and electron energy loss. So when you apply electric field, electrons gain energy due to electric field and they lose energy to phonons. And at some point when you keep increasing the electric field, energy gain due to electric field is always greater than energy loss to phonons. And this is the Froelich criteria for breakdown. So I'm not going to go into the details of how do we actually compute the breakdown field strength from first principles, but here we asked a different questions. And the question is, given accurate breakdown field strength for a set of compounds, can we come up with a machine learning model that actually helps us predicting this breakdown field in a much more efficient manner and using features just based on the chemistry? So to test this, we created a database of 82 binary octets from first principles. It was very laborious and took us long time. And once we have this breakdown field strength data from for 82 binary compounds, we actually validate these results against experimental available data. So for all of them, experimental data is not available, but for a dozen or so, reliable experiment results are available, and we use that to validate our computed results. And after that, so let me show you the final results. So this is the computed theoretical breakdown field strength for all these 82 binary octets. And here the compounds are actually grouped in different classes. So we have alkali metal halides, and then transition metal halides, group 4, group 3, 5, 4, 6 semiconductors, and so on. And in each group we have arranged compound according to the anions. So we have lithium fluoride, lithium chloride, bromide, iodide, and so on. So you get the idea. And the breakdown actually varies over about 3 orders of magnitude. But when we look at this data, it already gives us first hint that there are systematic trends with respect to chemistry. And the question we are asking is, can we really learn something from these trends? And can machine learning help us in learning these trends? Can we come up with a machine learning model for breakdown field? So this is our property data set computed from first principles, and these are some easily accessible attributes which can be computed in a straightforward manner as compared to the breakdown field strength itself. And these are selected based on mechanistic understanding. So the question we are asking is, can we establish a mapping? Can we have a functional form that at the end of the day allows us to write the breakdown field as a function of a subset of these features? So to do this, we first expand our data set in a nonlinear feature space. So we consider 12 prototypical algebraic functions, and these are listed over here. And then x can be any of these features. So let's say if it's band gap, then we consider band gap, inverse of band gap, square of band gap, and so on. So we have 8 primary features and 12 prototypical functions. So that gives us 8 times 12, 96 features of one function. And then we can cross multiply these 96 times 96, and then we select unique ones out of these, and then we again take functions of 3 features, and that's much more. So and then we identify unique ones there, and we add them all up, and at the end of the day we have about 180k or so compound features. Now out of this large data set, our goal is to find features that show very good correlation with the breakdown field, at least the predictive correlation. So for that we use lasso, and on Tuesday you have already seen the details of lasso in Jan's talk, so I'll not going to go into the details again, but I'll just say that we start with this one about 180K or so compound features, and at the end we using lasso we find 36 features which show very good correlation with the breakdown field, and these are listed over here, at least some of them, top 10 and last one. So so you see that there are many features that show very good correlation with the breakdown field, but we select we use our human intuition to select the second one, and there are two reasons. So the rationale behind selecting this one is that this is the simplest one of them all, and then second one is we can attribute some physical meaning to it, so we understand why so it's very easy to understand that why band gap and phonon cutoff frequency should be there in predicting the breakdown field strength. So we take that feature and we compare it with the predictions made with DFT, so that's the correlation. So on the x-axis we have DFT predictions of the breakdown, DFT computed value of the breakdown, and on y-axis we have machine learning predictions, which is given by our machine learning analytical form, expressing band gap as a function of expressing breakdown field as a function of band gap and phonon cutoff frequency. So that's the machine learning prediction. So in the red it's the training set, yellow is the test set, and then white diamonds are other compounds which were not part of original binary octet. So we wanted to try it on something new and see how it works out, and it seemed to be working well. Now if you look at this correlation, it's not perfect, but it's interesting that we find a good correlation over about 3 orders of magnitude, and this is already very powerful, because now what it means is that we can actually predict a breakdown field strength which is much more difficult quantity to compute by just using these two simple features, band gap and phonon cutoff frequency. But at the same time there is a disclaimer that this is based on heuristics, so this is not a law, so we should not try to read too much out of it, but it can be practically useful in exploring large chemical space and screening compounds which show high breakdown field strength. So that's what we do next. So we go to the perovskite compound space. So there are several thousand of perovskites, ABX3 type of compounds, and we identify which one of these are stable in perovskite structure, and we look for insulating compounds so have finite band gap, and there are about 200 of these, and then we use this machine learning identified form to predict the breakdown field strength using the band gap and phonon cutoff frequency on this set. So the results are shown here. So these are on x-axis and y-axis are our two features, band gap and phonon cutoff frequency, and the contours are the breakdown field strength. The gray region below the dashed line is actually the where we expect that machine learning model to work, and that means in our original 82 binary octets, most of the compounds that were in the training set had their band gap and phonon cutoff frequency falling in this range. So if we are going out of this gray area, we are really going out of the domain of machine learning model. Now interesting thing comes out of this is that when we go higher in band gap and higher in phonon frequency, that's the that's the region where our highest breakdown field strength compounds reside, and many of these compounds actually have boron in them. So this is interesting to note that boron containing compounds seem to show very high breakdown field strength, and we are currently looking into this in further detail. So this brings me to the end of this first example, and summarizing, I showed you that we have used first principles based framework to compute breakdown field strength for 82 binary octets, and then we use this data to train a machine learning model that then allows us to compute breakdown field strength just using two simple attributes like band gap and phonon cutoff frequency. Then we use this machine learning model on perovskites to screen large compound space, and at the end of the day we find that boron containing compounds seem to be promising for high breakdown field strength applications. So now let's switch gears a little bit and move on to the next example, and this is multi-fidelity machine learning models for band gap predictions. So let me explain a little bit about what do I actually mean by multi-fidelity. So let's say we have a property P which can be computed using different methods. So method A, method B, and method C. And these different methods have a hierarchy in both cost and accuracy. So method is most accurate, at the same time it's most computationally expensive. On the other hand, method C is very cheap in accuracy and cost. Now we need to compute this property for a set of, let's say, 1,000 compounds. And question is, what method should we be using? And if we use method A for everything, then very quickly we will exhaust our computational resources, and at the end of the day we'll have only a handful of data points. On the other hand, if we use method C for everything, then it will only help us get the wrong answer 10 times faster. So there is this, given a limited computational budget, how do we really control this trade-off between computational cost and accuracy to make the best predictions at the highest level of fidelity? So that's the question we are asking, and this has implications for material genomics applications when you are looking at really large chemical spaces and also looking for functionalities, so rational materials design. And in this talk, I'm going to take a specific example of band gap to explain how machine learning can help us do this. And band gap is a key property for a range of applications. Some of are highlighted here. So we have catalysis, scintillators, energy harvesting applications, and energy storage applications, and so on. And then there is also a hierarchy of DFT and beyond methods that is available that allows us to compute band gap at different level of accuracies. And this is very beautifully captured in Purdue's illustration of Jacob's ladder of DFT exchange correlation functionals, where at the methods at functionals at the lower side of the ladder, so local and semi-local exchange correlation functionals are very computationally efficient in a relative manner, but at the same time it's well known that they severely underestimate the band gap. As we go higher up, we systematically go up in both accuracy as well as computational cost. So if we have band gaps at different levels of fidelity, how do we combine these in a machine learning model to make, then at the end of the day, make best predictions at the highest level of fidelity? That's the question we are trying to address. And in this example, I'm going to take two specific levels of fidelity. So low fidelity is given by PB band gaps, and high fidelity data points are going to be HSE06 band gaps. And for materials, we take alpha-solites or double perovskite halides of A2B, B prime, X6 type, where elemental species at A, B, B prime, and X are shown here. And in this data set, we have about 600 or so alpha-solites, and for which we compute band gaps using, so we compute PB band gaps for all of them. And then we take random subset of 250 compounds and compute HSE band gaps for this. And then we take 200 PB and 200 HSE data points and use it in the training. And remaining 50 HSE data points are not touched during the process of training and are only used for testing. And predictions are made on the rest of the data set. So for features, we use elemental features, like simple elemental features like electronegativity, ionization potential, Slater's empirical radii, and Petty-Force-Mendeleev number for each of these elemental species occurring at A, B, B prime, and X sites. So there are 4 species and we have 4 different features. So each compound is represented as a 16 component feature vector. So let's say this is our feature space, and these are the compounds for which we do our low fidelity PB calculations. And then we select a subset of these and we compute HSE band gaps for these. And then we use this for training and then train our machine learning model, and for the rest of the compounds we make predictions. Specific choice of these features was motivated by prior work by others as well as our prior work. So let me give you some details about the machine learning model that we used. We use co-kriging based on Bayesian framework. In the co-kriging model, the output of high fidelity is represented as a scaling parameter times output of low fidelity plus the difference between the high fidelity and low fidelity. And so the low fidelity model and the difference model are treated as two independent Gaussian processes. And correlation between two compounds represented by x and x prime feature d-dimensional feature vectors is given by the squared exponential functions where theta j are parameters. If all theta j are same, then it's an isotropic kernel. And the full covariance matrix looks something like this. So the important thing to note here is that we have correlation within the low fidelity data set, within the high fidelity data set, as well as the cross correlation between low fidelity and high fidelity data sets. And unlike conventional Gaussian process regressions or kernel ridge regression where you have one set of hyperparameters, here you have two independent Gaussian processes, so you need to estimate two sets of hyperparameters as well as the scaling parameter and all the theta j's which are solved numerically. So once you have all the hyperparameters and parameters identified, then you can make predictions for a new compound X star using these formulas. An advantage of using the Bayesian framework is that we make predictions given by these means, but we also get error bars. That is the confidence level in those predictions that our model has. So this is the final result, and let me walk you through this. So this is our training data set. So we have 200 PB and 200 HSE data points, and then we select a subset of these. So N sub C, that is C is for cheap and E is for expensive. So we select NC number of PB data points and NE number of HSE data points, and then for different combination of these we train different machine learning models, and then we evaluate the performance on the unseen data. So here what is plotted is the RMSE error on the validation set or unseen data that was never touched during the process of training. On the y-axis we have number of PB data points, and on the x-axis we have difference between the PB and HSE data points. So for the bottom left we have 130 PB data points that our model was trained on, and the difference is 20, so we have 110 HSE data points. So that's the combination we used to train the model, and that was the test set error. And here, because the difference is 90, that means we have much less number of HSE data points, and the prediction performance is actually much worse as compared to this. So if you plot this data this way, then the dashed line represents the model that were trained on a constant number of HSE data points. So all these models lying on this dashed line actually had 100 number of HSE data points. So by the time we reach about 130 or so, we are already saturated in terms of performance with respect to PB data points. But if we go along the diagonal here, we see that performance with respect to HSE data points systematically increases. And by the time we have about 150 HSE data points in our training, we are already making very good predictions where error on the test set is less than 0.1 EV. So that means out of 600 total compounds, we only need calculations for 150 or so. So that's a 4-fold increase in computational efficiency. Now this plot can be used to actually in a limited computational budget, this plot can be used to make decisions at, given your computational budget, where you want to stand and how accurate your predictions are going to be. Now let's take a closer look at some of the results. So So here for selected panels, I have plotted the parity plots between DFT computed HSE band gaps and machine learning predicted HSE band gaps. And as you see, initially when we are at the bottom part of this diagonal, our means are not as good, but also error bars are high. But as we systematically add more data points, not only the means are getting better, that means more and more points lie on the parity line, but also that error bars are shrinking. So the model is making good predictions, but it also has more confidence in those predictions. So let's compare it with state of the art. So it's a general practice to actually fit such straight lines. So on x-axis we have our, let's say, low fidelity model, and y-axis, in this case it's an experimental data, but it could as well be HSE band gaps or GW band gaps. And in many cases it's possible to fit a straight line, and this is very efficient. But if you fit a straight line, then you usually get much larger scatter. So the predictions you are going to be making will not be very good. On the other extreme, one can use PB band gaps as a feature of the machine learning itself. So recently, Lee and co-workers showed that GW band gaps can be predicted very accurately if you use PB band gaps in addition to the atomic features in the machine learning model. In this particular case, they use support vector regression. And you see that predictions are really good. But the deficiency is, if you are going to use such a model for much larger chemical space, then for every prediction you are going to make, you need a DFT calculations, because you are using PB band gap in the machine learning model as a feature. So the co-Kriging model that was presented actually gets combines the best of these both worlds. So you can make much more efficient predictions. At the same time, you don't really need PB band gaps as a feature. If you have low fidelity data, it can always include it, but if it's not there, then still predictions can be made. So it's not a limiting restriction. So with that, we are at the end of the second example. So I have showed you that an example where we used PB and HSE band gaps and trained a machine learning model to predict HSE band gaps for a set of alpha-solite compounds. I do need to mention that alpha-solite compounds are a special case in that most of them are cubic. So there are really no lattice distortions. So if we have lattice distortions like in perovskite oxides, then I anticipate that machine learning band gaps will be much more difficult, because then your atomistic features cannot just predict the band gaps. You also need to consider for the lattice distortions. But such machine learning based models can be very useful in high throughput chemical space explorations, as well as they can work as intermediate filter for application specific screening. So going forward, what are the critical steps? And in my point of view, I think the real power of machine learning is training the model in an adaptive manner rather than training just one-shot predictions. And so we should use uncertainties to adaptively refine the model, and in such sort of framework of active learning. And then comes a challenge of balancing the trade-offs between exploration versus exploitation. So what do I really mean by that is, let me explain. So we start, in every machine learning model, we start with some given data, and then we choose our features, we do feature engineering, feature selection, and so on, and then use a machine learning model and train the model, do the training, testing, validation, and so on. And then in some cases, we also have access to uncertainties in those predictions. Now, we should be able to use these uncertainties to predict the next candidates, which when included in our original database will and then we do retraining, it will actually iteratively refine the model. And this next training set, next candidate selection can be done in two different ways. So the first one is, most oftentimes we are always looking for a property that we would like to optimize. So we are looking for some specific compounds. So either use machine learning model to predict that property and select the compounds with optimal property. And that would be exploitation of the model, because we are using machine learning model to identify the compounds. But the second approach is exploration. That is, we select those compounds for which machine learning model has least information. That means the uncertainties are high. Machine learning model is not very confident about those compounds. If we use those compounds in the model, then it will have more information, its domain of applicability will expand, and in the next round it will be able to make better predictions. So that's kind of the exploration. So I really think going forward, this type of adaptive design is the key, and it can really help us in exploring materials chemical spaces. So this is basically what I said. If we are looking for a target property and we want to optimize this property, we want to maximize this property after n cycle, this is our nth best, then we have two different choices. Choice one is where our property is high and machine learning model is very confident. So if we choose this would be the exploitation choice. But if we choose another choice 2, that is the uncertainties are high and machine learning model is not very confident, that would be the exploration choice. Another critical another area where machine learning model can be particularly useful are multi-objective optimization. So in material science, we are often interested in a number of properties rather than just one property, and these properties have conflicting relations. For example, for for energy storage application, we want band gap and dielectric constant both to be large, but band gap is inversely correlated with the electronic part of the dielectric constant. So if you optimize one, another one goes down. In such situation, we are looking for Pareto optimal compounds. And so how do we use machine learning to efficiently explore Pareto optimal fronts in high dimensional chemical spaces? And I think machine learning can be really useful in addressing this type of problems. And final area is, of course, how do we put more domain knowledge in the machine learning models itself. Right now, we use descriptor or features as one way to put domain knowledge or physics inside the machine learning model, but are there any better ways of doing it? For example, if you are trying to understand a property, let's say critical temperature, is it better to just predict that property, or is it better to learn some parameters of a Hamiltonian and then use that Hamiltonian to predict the property? So I think these are the critical questions that we need to address going forward. And of course, we can learn from what has already been done in the other communities. So statistical learning and engineering communities has been using these machine learning models. And I think materials problems are different, but at the same time, I think there are many methods that can be imported to materials problems. And the coke rigging method that second example that I showed, this is how actually the airplane wings are designed in aerospace industry. And it has been around there for decades, but in materials community, it's very new. So with that, thank you very much for your attention, and I would like to thank my co-workers and collaborators at Los Alamos as well as in Rampe's group at University of Connecticut, and also would like to thank my host at Fritz Haber Institute, Matthias Scheffler and Luca, and I would also like to thank whole Nomad team for organizing this wonderful event. Thank you very much.